Hello everyone, welcome back to another SLHL IB chemistry video. Today we're going to be looking at energy cycles in reactions under reactivity 1.2. So let's just get started with a little recap of reactivity 1.1. So you may or may not remember the profile level diagrams in which we see the energy which is either lost or gained by a system depending on if the reaction it has undergone was endothermic or exothermic. Now, the breaking of bonds takes energies to make, which means that this is an endothermic reaction, taking a lot of energy, as we see here. That's a very high activation energy curve. So it takes a lot of energy for this to occur, meaning that this reaction absorbs energy. Differently, to make bonds, these will emit energy. Energy is released from the system, as you can see by this decrease in the profile level diagram. Now, this is important to keep in mind when we are calculating the change in enthalpy of reaction, because to calculate this, we will need the formula, which is delta H, or change in enthalpy, equals the sum of bond energies broken minus the sum of the bond energies made. So the energy of all the bonds that are broken subtracted by the energy of all the bonds that are made. Now let's just take the example of the hydrogenation of ethyne. So let's take some space to draw this out. So hydrogenation, we are adding two hydrogens, and this turns into ethane. So this is a skill that you will need to have to use the bond enthalpy values, which will be given to you in the data booklet, and essentially plug these into this formula. So you'll have to be comfortable with doing this. So in terms of the hydrogenation of ethyne that we can see here, as we see, it's bonds broken minus bonds made. So let's just start by calculating all of the energy required to break all of the bonds of the reactants. So we have one triple bond between these two carbons over here, which has a value of plus 839 kilojoules. That is how much will be absorbed. We have two carbon to hydrogen bonds over here. So 2 times -413. Now, even though the breaking of a bond is an endothermic reaction, the the enthalpy energy of the bond enthalpy can still be positive or negative. So back to this, kilojoules. And then finally we've got two hydrogen to hydrogen bonds, so 2 times 432, which gives us 864 kilojoules. Add these three values together and we get 2,529 kilojoules. Now, let's add up all of the energies of the bonds that are made, so of our products. Yet again, we have one carbon to carbon bond, which will be our negative, since we are subtracting. This will be negative 347 kilojoules. Then we have 6 carbon to hydrogen bonds, because remember this is no longer ethyne but ethene. So ethane, apologies. And we will have to do negative, because yet again, reactants. 413 times 6, because we got 6 of those bonds, giving us negative 2,478. Now we add these two values together, giving us negative 2,826. So bonds broken subtracted by bonds made. Bonds broken 2,529 minus 2,826, which gives us an overall change in enthalpy of negative 296 kilojoules per mole. So this is an example of the kind of work that you will need to be familiar with when it comes to calculating bond enthalpies. If you are to calculate the bond enthalpy of a multi-step reaction, as it is stated here that you may or may have to be able to work with, the overall bond enthalpy of a multi-stage reaction is simply a sum of all of the bonds broken subtracted by all of the bonds which are made in this multi-stage reaction. So you can do this little thing that we did here for the hydrogenation, but if this reaction were to have a second step, we would then just go through the same process again, add or subtracting the values as necessary. And next up, the final point in reactivity 1.2 for the standard level students will be in terms of Hess's law. So Hess's law is essentially this formula which we have just learned. So it states that the total change in chemical energy is equal to that which is either lost or gained by the system. And this law is obviously very useful for us to predict the average changes in enthalpy in a reaction. But in real life, even with the most precise measuring equipment, we will see that the calculated enthalpies, which we will find, will not be the same as our ones which we find using the bond enthalpies, say, given in our data booklets. And this is because although energy cannot be created or destroyed, it can be lost or gained by a system. And what will happen is that as bonds are destroyed, energy can be lost through heat, meaning that not all of the energy will be maintained in the system. So what will happen is that the value that we calculate may not be the same, theoretically, as the one that we will see practically. Now, that is all that we need to know for Reactivity 1.2. Thank you for watching, and I hope that this could be helpful.